If you've ever been interested in mathematics, chances are you've encountered the issue of communication. You learn something or see something that really truly fascinates you, and so you go to your friends and family and loved ones to talk about it, but it just isn't possible, or at least it isn't easy. Some math requires the understanding of strange or arcane concepts, and others still are barricaded simply by jargon and terminology. It's a beauty to you, it's a chore to others. I also think that if you faced this problem, then you may have come to appreciate and really delight in those beautiful, if few, pieces of math that come across just how you want them to. No jargon, no prerequisite, just the ability to imagine. One of my favorite pieces of such math is the Pythagorean theorem, not just because of how simple it is to convey, a squared plus b squared equals c squared, but also how nice it is to picture. This is one of those pictures, originally thought up by Euclid centuries ago. There's a lot I could tell you about this from a math standpoint, when it was made, how this actually proves the Pythagorean theorem. But rather than all that, rather than look at this like some kind of mathematical object made to solely prove a point, I want you to think of it like a work of art. Like something you'd see on display, framed and elevated against a wall. Something that Euclid may have spent months or even years on. Do you see how that perspective paints the diagram in a whole new light? It has subjective qualities, things that you may find beautiful that not everyone else does. Now imagine that in addition to the artistic beauty, Euclid's art has mathematical beauty as well. It may be more hidden, more subtle, but just know that this diagram, constructed of exactly 13 straight lines, proves one of the most well-known theorems in all of mathematics. Isn't that just magnificent? Now, all cards on the table, this is not a video about the Pythagorean theorem. While we will talk about some nice diagrams and some named mathematicians like Euclid, what I want to talk about is another part of mathematics that, like the Pythagorean theorem, is really, really beautiful and not that difficult actually to describe. This is Euler's identity, a short little equation that relates the most important numbers in all of math in one concise delivery. What I want to do is talk about the millennia of beauty in this equation. The 5 numbers each have way more under the hood than is present just in their actual symbol. This is Euler's identity, a culmination of mathematics driven by insatiable curiosity and one of the most beautiful ideas across all of mathematics. Now, e is one of those numbers that feels like it's always taking a backseat to pi. If you've heard of both of them, you may know that they're both irrational or even that they're both transcendental. But whether you've taken many math classes or very little, you kind of have a loose idea of what pi is. It relates to circles somehow. But e doesn't have that kind of quick connection the same way that pi does. So what is e? Throughout the 17th century, several mathematicians worked with this number, mostly unknowingly. In 1618, Scottish mathematician John Napier worked extensively with the natural logarithm, which, unbeknownst to Napier, has e as its base. A few years later, in 1624, English mathematician Henry Briggs approximated the log of e, but didn't give e any special name. Then, both Belgian Gregory of St. Vincent and Dutch Christian Huygens encountered e with regards to functions in 1647 and 1661, respectively, and later in 1668, German mathematician Nicholas Mercator coined the term natural logarithm to refer to the special log which Napier had worked with. But across half a century of exploration and direct confrontation with e, none of the above mathematicians thought to make e an official constant, or at least they're not the ones credited with its official discovery. E did not come out of work with logarithms or work with functions, but instead it came out of a completely ridiculous question. Say you have some money to invest. Bank 1 promises you 100% interest compounded once a year. Bank 2 offers you that same 100% interest compounded twice a year. Bank 3 compounds 3 times a year, and so on, where Bank N compounds N times. As N increases, as you compound more and more frequently, the amount of money in your account at the end of the year will be greater and greater. Bank 365 compounds your money every day. Bank 8,760 compounds it once per hour, and all the way down at Bank 31,536,000, your money is being compounded every single second. In 1683, Swiss mathematician Jacob Bernoulli wondered if you get to the end of the line of banks, to bank infinity, if you deposit $1 into that bank, how much money would you have at the end of the year? We can see that as we move up the banks, we end up with more and more money, but we increase in smaller and smaller intervals. So which force wins? Do we end up with some finite amount of money at the end, or do the banks spiral out of bounds? As you may have guessed, bank infinity does in fact give us a finite amount of money, and that amount is precisely E dollars. Now, at the time, Bernoulli didn't actually know this number, but he knew something just as important, which is that there was a number. That is, as you get to bank infinity, there is an upper bound that your money will hit. It won't spiral out of control. Around 1731, Swiss mathematician Leonhard Euler started using the notation E, finally giving a name to this number. But contrary to what you might think, he didn't name it after himself, and likely didn't even name it because it was exponential, E for exponent, but just because he was partial to vowels, and he was already using A at the time. And so, after a spurt of a century or so, E, a number tied to the mathematical idea of progression and growth, and the first piece of our formula comes into focus. Now, despite being just one vowel over, the number I is unlike any other number in this formula. Quadratic equations are a type of equation with a squared term, such as this one. By the 16th century, many civilizations had searched for and succeeded in finding a method for achieving the solutions to any quadratic equation, namely the quadratic formula. Now, this formula has a beautiful and very lovely derivation. If you subtract c and divide through by a from any general quadratic equation, you can interpret the resulting equation geometrically. A square with side lengths x, and consequently area x squared, when combined with a rectangle of sides b over a and x, must produce a shape with area negative c over a. Slicing the rectangle in half and reorganizing the shapes, we get almost a square. We just need to fill in the little bottom corner, which has sides of b over 2a and thus area b over 2a squared. From here, since the left side of the equation is just the area of the shape, we can say the area of the square is now the product of its sides, x plus b over 2a squared. And then it's a little bit of algebra to get the final formula we know and love. There is not, however, as clean a derivation for the next level up, the cubic formula. Just like many civilizations had already found the quadratic formula, many struggled in search of its cubic counterpart. In Italy, around 1510, the first of many steps towards the cubic formula and complex numbers starts to take shape. A mathematics professor, Scipione del Ferro, had managed to solve the depressed cubic, a variant of the original with no squared piece. Del Ferro shares this secret with his student Antonio Fior on his deathbed in 1526. Fior gloats about his new ability to solve depressed cubics, drawing the attention of many mathematicians, including Niccolo Fontana Tartaglia, to whom Fior openly challenges. However, having heard that a solution to the depressed cubic exists, Tartaglia had dived into his own work seeking it for himself, and, with his success, bests Fior and his challenge. Tartaglia's victory captures the attention of one Girolamo Cardano, who coerces the formula out of Tartaglia in 1539, but only after swearing to never share it with anyone, per Tartaglia's insistence. And here we come to the next big step in imaginary numbers, which is the flaw. As Cardano and Tartaglia played around with this formula, despite there being real numbered solutions to some cubic equations, the formula would produce incorrect answers. When I say incorrect, I mean the square roots of negative numbers, which at the time, because Cardano and Tartaglia had no means to deal with these numbers, would just render them as non-existent. This is an error in the formula. It did not work. Now, this is a really crucial moment for the discovery of complex numbers, because I, the complex unit, is defined to be the number such that I squared is negative 1, or in a way, I is the square root of negative 1. It is the square root of a negative number. But again, because neither Cardano nor Tartaglia nor anybody in Italy at the time had any means to deal with this, they just ignored this case. Until 1555, when Raphael Bombelli picked up where these mathematicians left off. Bombelli reasoned that since the square root of a negative number can't be anything positive nor anything negative, he lets it be its own kind of number, written as the product of some real number and the square root of negative 1. Not only does this solve the case Cardano and Tartaglia had struggled with by allowing the roots of negatives to cancel each other out, but it was a step towards the rich field of complex numbers. Rounding out the ground of the exploration, René Descartes utilizes the term imaginary numbers in reference to Bombelli's numbers, to which Euler popularizes the notation I, furthering his love of vowels. And so I, an entirely new kind of number, enters the equation, the two vowels paired together. Now, while he was responsible for quite a bit of mathematics, Euler did not do everything, and he was predated by pi by several thousand years. So we're all on the same page. If you draw a circle and its diameter, pi is the ratio of that circle's circumference to that diameter. Or, another way to think about it, pi is how many times you would need to walk along that diameter to fully walk around the circle. Unlike e, though, approximating pi is pretty straightforward thanks to its roots in geometry. If you draw a circle, then you can start laying pieces of string across its diameter and its circumference, and you can compare the number of each that you use. If you use 2 pieces of string to cover the diameter, you'll see that you use a little more than 6 to cover the circumference, telling you that pi is a little bit bigger than 6 over 2 or a little bit bigger than 3. Now, of course, we can get much more accurate than that, and that's exactly what ancient civilizations did. The Babylonians approximated pi at around 3.125, sometime between 1900 and 1680 BC, and the Egyptians increased that number to 3.1605 around 1650 BC. These are still pretty far away from the 3.14 that we know now, but they were really great for the time. Two major methods of approximating pi come from two mathematical titans of their respective era, Archimedes in 250 BC and Zhuangzi in 480 AD. Both mathematicians began to approximate pi by drawing shapes. For thousands of years, one argument for bounding pi was to draw a hexagon inside a circle and a square outside, then calculate the perimeter of each. The diameter of the circle was constant, and the hexagon provided a lower bound for pi, while the square provided an upper bound. What Archimedes did was improve upon this method by making the binding shapes more and more closely approximate a circle, changing both shapes to dodecagons, then an icosatetragon, then a tetraconta octagon, then finally feeling satiated on an neoconta hexagon. This method confirmation that pi was greater than 3 and 10/71 and less than 3 and 1/7, or in decimal, greater than 3.140845 and less than 3.142857. Now, these are fine, but if you want to get more precise there, and if you're not satiated with these approximations, then let me introduce you to mathematician Liu Hui. Sometime around 265 AD, Chinese mathematician Liu Hui was also approximating pi, and with a similar start to Archimedes. He inscribed a hexagon inside a circle, but rather than tackle perimeter, he went for area. Liu appended rectangles to the edges of the hexagon. This created excess area, which he used to provide an upper limit to how big pi could be. Now, Liu Hui utilized these shapes to sandwich pi between a 96-sided shape and a 192-sided shape, obtaining that pi must be greater than 3.141024 and less than 3.142704. Content to stop there. Zhuangzi was willing to dive even deeper into approximation, continuing this method to staggering lengths, bisecting the hexagon 12 times to attain a dimeria, tetrachilia, pentahecta, heptaconta hexagon, or a shape with 24,576 sides. This allowed Zhu, by hand, to bound pi between 3.1415926 and 3.1415927, a record that would stand for over 9 centuries. Now, talking about the beauty of 1 and 0 is a little strange because it's like talking about the beauty of numbers. At some point in history, we decided to start counting things, and we decided that 1 would be what we called the first thing, and 0 would be that kind of boundary point along the middle. What we didn't unanimously decide on from a mathematical standpoint is what base system to use. All the numbers present so far in this video are in base 10, as opposed to base 2 or base 16, which lots of computers work with, those being binary and hexadecimal, or a combination of base 5 and base 20, which you can hear when speaking French. In any base number system, each digit represents how many copies of various powers of that base you have. For instance, the number 24,576 in base 10 has 6 copies of 10 to the 0, or just 1, 7 copies of 10 to the 1st, or just 10, 5 copies of 10 squared, or 100, and so on. However, the same digits can mean something totally different in a different base number system. In base 8, for instance, this number would have 6 copies of 8 to the 0, 7 copies of 8 to the first, 5 copies of 8 squared, or 64, and so on, getting a far smaller result in base 10. Something that's absolutely delightful about these different bases is that, as illustrated above, the depiction of the number is inherently tied to the choice of base. Every digit can mean anything except 1 and 0. The numbers 1 and 0 are written the same way in every single base number system, and they are the only numbers with this property. They are the heart of every number system and absolutely have earned their spots in Euler's identity. So, with all these numbers floating around in the mathematical lexicon, where do we go from here? At this point, it might seem natural to go and derive Euler's identity. I mean, we have all the pieces. We've done an awful lot of work finding them. The thing is, I don't want to emphasize the math here. I don't want the main takeaway of this video to be how Euler's identity is derived. I wanted to emphasize the scale and the grandeur of the mathematics, how 5 numbers, each with their own storied histories that develop mostly in isolation from one another, not only combine into an equation at all, but one that is very simple and very, very elegant. This is Euler's formula, born in 1748 in Euler's Introductio in Analysis Infinitorum. Originally derived by Euler using Abraham Dembrove's equations, even Euler himself didn't think to simply plug in pi for theta to arrive at his identity. The identity simply came as a consequence, and was named Euler's identity after the man who discovered the formula. Now, again, I don't want to emphasize the math here, or even the formula. Just like at the beginning, with the Pythagorean theorem, it's not the formula that's beautiful, it's the image. If I take a point in the xy plane, and let its x-coordinate be the cosine of some input t, and the y-coordinate be the sine of that input t, as we vary t, our point traces out the path of a circle. In fact, if we track the height and width of this point as it travels along, we can see the sine and cosine curves emerge. Now, remember those numbers that Bombelli found, that a plus bi? If we wanted to plot those numbers on a graph, we use the complex plane, where the horizontal axis, instead of representing the x-coordinate, represents the real valued piece, and the vertical represents the imaginary piece. Now, choosing an input theta for Euler's formula produces one of these numbers, something of the form a plus bi. Since cosine is the real number part and I sine is the imaginary, we can think of cosine being the x-coordinate and sine being the y, which means that e to the I theta, just like our point that we plotted, traces out the path of a circle, because its x-coordinate is cosine and its y-coordinate is sine. And more so than just that, the input theta is the amount by which that point rotates. When theta is 0, the point is to the right, situated at positive 1, since it hasn't rotated at all. As theta increases, the point starts to spin around counterclockwise until we rotate pi radians, landing at negative 1. E to the I pi is negative 1, or e to the I pi plus 1 is 0. Ignore the math, ignore the symbols, ignore the formula and the graph and the identity. Just look at the picture that we drew. Look at how simple it is, at how all we need to do is let the point go on its way, and it shows us one of the most beautiful ideas in all of mathematics. This is what a staggering amount of math is: elegance and beauty. While there will always be those ideas that get lost in translation, there will always be those that do not, those that come off exactly as you want them to. The number e was discovered because Jacob Bernoulli asked a ludicrous question about a very real idea, and that's beautiful. The number I and complex analysis was birthed out of Del Ferro and Fior and Tartaglia and Cardano and Raphael Bombelli's monumental choice to create an entirely new number, and that's beautiful. Pi, known for thousands of years and approximated past any reasonable practical purpose, continues to fascinate and govern one of the most simple and beautiful shapes in all of geometry. 1 represents the genesis of all of mathematics, and 0, one of the most powerful numbers, its first antagonist. And that's beautiful. And all of these titans, all of these giants, are not only present in the same equation, they each contribute. I sets the stage in the complex plane, Pi adds the circle, E expresses the growth and progression around that circle, and 1 and 0, the core numbers of arithmetic, remind us that even this seemingly obscene cacophony of symbols can have a very simple and very familiar meaning. E to the I pi is -1 because as you walk around a unit circle, -1 is simply where you end your walk. E to the I pi plus 1 equals 0 because we chose to rewrite the equation, because we felt it more beautiful to include a 0. E to the I pi plus 1 is equal to 0 because of Bernoulli, and Del Ferro, and Fior, and Tartaglia, and Bombelli, and Archimedes, and Liouville, and Souchongzhi, and Euler, and every other mathematician who helped contribute to the field at large. This simple equation is the culmination of millennia of effort and progress. It includes irrational numbers and imaginary numbers and invariant numbers, and it's as simple as a circle. Just like the Pythagorean theorem is as simple as a triangle.